Hi everyone, this is my Lab 5 for Physics 2 at Georgia Tech, in which we're going to be examining a falling magnet through a solenoid. So we're going to be examining the effects and interactions between the different forces, for example gravitational force and magnetic force, when a bar magnet free falls through an aluminum tube. I expect for there to be an induced current in the conductor, which is the aluminum tube that I'll be using, and then an induced magnetic field will be created to oppose the change in flux, which is due to Faraday's law. I'll also be applying Newton's second and third laws to relate the forces in the code and therefore create graphing for my results. Some of my general results, though, were that I observed the time for the magnet to fall through the conducting tube to be 0.9 seconds, which is significantly less, more or less, than the time that my simulation calculated. My simulation calculated for the magnet to take 3.238 seconds to fall through the tube. So for my data and observations, I got the length of the tube to be 0.298 meters, and then for the radius that I used for my calculations, I added up the width of the foil and the inner radius of the tube to get the full radius, which was 0.032 meters. And then I used my value of mu from Lab 3, which was 1.31 times 10 to the 1, to calculate magnetic field. However, I had some issues with this lab, so my value is slightly off, which created some issues, I believe, in my calculations, which I'll discuss later. After a few trials, as I mentioned before, I got my average time for the magnet to fall to be 0.9 seconds, and then I also observed that the magnet seemed to fall slower in the tube than without the tube, which is due to the induced current. So here we can see the different calculations, the significant ones that I did in my code. So the first one is a definition function for magnetic field of a dipole. And I used this to calculate the force that was the magnetic force exerted by a falling magnet. And then the second code, I have an equation for the to find the change in flux. And then I also use Newton's second law in the third picture to update velocity and position using the net force that I calculated. And then for my simulation, we can see to the left the graph that I have for velocity versus time. So the line flattens out, which suggests that the near constant velocity shown by the graph indicates that the net force was equal to 0, which makes sense because the magnetic field and the magnetic force and the gravitational force should nearly equal 0 because it's causing the magnet to fall a bit slower. However, it's not completely suspended in air. The simulation also doesn't account for air resistance, though, which may have been a factor in my real-life simulation. I observed that my observed results were less than my results that were calculated by the code, and this I would think is due to my large value for mu. And this is because the value of mu would cause my magnetic field to be larger, and because the magnetic field is large, it would thus cause, it would take longer for the magnet to fall through the tube, because magnetic field is the only thing that is able to change in the change in flux equation, because the area of the tube is fixed. And as for intensity of coloring, I know that the induced current direction is in the direction of negative magnitude of change in flux with respect to time. So I deciphered that the induced current would be counterclockwise by the right-hand rule. And then as I looked at the tube from the top, I got that the red coloring would equal counterclockwise and blue would be clockwise. And in addition to this, there'd be no change in dynamics if the magnet was dropped in the opposite direction, because we always know that the induced current will oppose the change in flux. In conclusion, if resistivity of the conductor approaches 0, the induced current and magnetic field or magnetic force increases to oppose change in flux. Therefore, the magnet is going to flow a bit slower, or it's going to fall a bit slower. And if there's holes in the tube, there would be no current in the rings because it can't flow continuously, which I thought of as a current running through a battery through wires in a circuit. So therefore the magnet would also fall more quickly because there's not as many rings with an induced current continuously flowing through it. Thank you.